Welcome back. Hope you guys had a nice break. First to some structure. As you know, the R4 grading period has ended. Please be quiet. Guys, what's going on? Okay, are we settled? You need a pencil still? Okay. R4 grading period has ended. We ended it with the test that we started last week, and I recognize that there are some people who haven't yet taken that test. As a result, the test will not be included in your R4 grade. I expect your R4 grade will then just be the homework up to this point. So I'm backed up a couple of assignments, but you should have a pretty clear vision of what your homework is. I'll be grading those and completing that in the next day or two. In the event that you're somebody who has a very poor grade on homework and your test grade would rescue your R4 grade, come tell me about that and I could do a special exception for you. But generally the structure is such that I have to add the R4 grade for everyone or for no one. So at this point, it's planned to be there for nobody. I will add it in as soon as we report our R4 grades, and you'll see what the impact is and have the opportunity to improve your grade or maintain your grade as you so choose. We are beginning today the next unit. It's chapter 8. It's called Similarity. But before we get into that, we need to get some algebra foundational stuff locked in. So I know this looks like patio, but we're not talking about furniture in your backyard. That actually says ratio. And what we're going to be working with is talking about ratios and how to use ratios to solve problems. So what is a ratio? It's a comparison of two or more quantities. So often we'll see ratios written as, for example, A colon B, right? Like 2 to 3 or 2 to 5 or 7 to 4. It can also be equivalently written as a fraction, like A over B. Or we could use letters like a name, A to B. Less mathematical. Importantly, ratios can be reduced or simplified. So for example, if I look at a music store that has 40 trumpets and I'm asked to exhibit a ratio of trumpets compared to violins, and it's got 24 violins, then I could express it as 40 trumpets to 24 violins. And that's a valid way to express it. Personally, I prefer the fractions. I think there's more value in those for what we're doing. And it's easier to see then how to reduce this. What number can be divided into both 40 and 24? 4 can go in. Anything further? 2. So in other words, 8 would have gone into it. We can take it all the way down to 5/3. That's the reduced ratio. And part of your homework will be to finish these other 3 problems doing the same thing, establishing what the ratio is, reducing it to its lowest form. Any questions on using ratios to simplify and come up with the simplest ratio? Okay, there will be times when we're actually looking to create a comparison of more than 2 quantities. And because it's more than 2, we have to adapt a little bit. We can still treat it as A is to B is to C, but we wouldn't write it as a fraction, right? Because the fraction would look like a club sandwich with 3 pieces of bread. That just seems wrong. So we're going to do a little bit of solving process for extended ratios because they do have a little different scenario. I like to think of it as we can treat it with the sum of weighted parts. All the different parts added together equals the whole. Here's a simple example. It is only 2 quantities, even though we're using the extended ratio idea. The ratio of 2 complementary angles is 3 to 7. Find the measures of both angles. So what's the whole? If we're saying these angles are complementary, what's the whole? 90. That's what complementary means. And then the sum of the weighted parts. So in other words, one part is in a ratio of 3 and one part is in a ratio of 7, but that's the reduced ratio. So it's not just 3 plus 7 equals 90, it's 3 times x and 7 times x. We don't know what that scale factor is, that x. But once I set it up as 3x's plus 7x's makes 90, I can then do some simplification and I get x equals 9. Again, the question asks us to find the measures of both angles. So 3 times 9 is 27, and 7 times 9 is 63. And if we take 27 plus 63, we see that that does add up to 90. We can use that same process to do explicit ones that have to be done by extended ratios. So look at number 7, please. The ratio of the measures of angles in a triangle is 4 to 7 to 9. Find the measures of the angles. So what's the whole in this case? Yeah, we know that the measures of all the angles in a triangle add to 180. Then we add these parts. 4x plus 7x plus 9x adds up to 180. 4 and 7 is 11, plus 9 is 20x equals 180. So x is 9. And then, got to answer the question. It asks for the measures of the angles. So 4 times 9 is 36 degrees. 7 times 9 is 63. 9 times 9 is 81. And sure enough, if you add those up, they add up to 180 as we expect. You've probably seen problems like this in your algebra class. Do you remember when they gave you like mixture problems? Johnny's got a 20-pound bag of nuts. If he's got 40% peanuts and 30% cashews, and the remaining 30% is macadamia nuts, how much of each does he have? That kind of thing. This is a good tool for solving those problems. Any questions on solving extended ratios? Okay, please flip to side 2. The reason we're going to use ratios is actually to solve proportions. What a proportion is an equation that states that two ratios are equal. And often it's written as something like A over B is equal to C over D. Right? It's a ratio equals another ratio. Once we get this equation, it's going to have some x's in it, for example. And what will then, go ahead. What we'll then be doing is solving that. And the primary tool we're going to use is something called the cross product property, which says that if this is true, then A times D cross product is equal to the other cross product, B times C. What that means for us here is for number 11, for example, we've got a proportion, a ratio equals a ratio. Therefore, we can apply the cross product property. If I multiply these two together, x times 2, that should equal the product of the other two parts, 4 times 7. In other words, 2x equals 28. Divide by 2, and I get x equals 14. In this case, that's all the question's asking for, solve for x. And I imagine there are some people in here who are able to just see that if this is 2/7, that the equivalent fraction, when the top has been doubled, the bottom should be doubled, right? 2/7 would be 4 over twice as much, 14. And that'll work sometimes. It gets a little more complicated here because you'd have to say to get 12 down to 10 is not just half or a third or anything like that. So it gets a little bit more complicated. It certainly gets much more complicated when we get down here. So please use this process of cross multiplication. That's primarily what we're doing here. Let's take a look at number 15, for example. Let's use our x piece first. We're saying that 2x minus 9 times 20 is equal to 10 times 9. I suggest you set it up in its multiplied but not distributed yet form first. Then distribute it. 40x minus 180 equals 90. This is a linear equation, so I'm going to get all my constants over to one side by adding 180. I get 40x equals 270. Divide by 40. And I get x equals 270 over 40. Can I reduce that? Well, I can certainly take the zeros off, right? Divide by 10. But this number is 3 times 3 times 3, and this number is 2 times 2. There's nothing that's going to cancel there. I could plug this one into a calculator. And because it's fourth, it would come out with like a nice 0.25, right? It's going to be, what was it, 26? No, 24. So it's going to be 6.75. But I would like to remind you that improper fractions, or fractions in general, are a really nice, precise way to give answers. You don't have to worry about rounding. You don't have to worry about whether you should round or whether you should leave it precise. It's always precise. Some of these will not come out to nice even numbers. Please know that going in. What about number 19? How is that one different? Yeah, we're going to have some quadratics going on here. So we're going to get x minus 1 times x plus 5. We know that's going to get us some x squareds. When I multiply two binomials, you'll remember that we do the first term, x times x. The last term, 5 times x. The inner terms, minus 1 times x. And then the last terms, minus 5, equals 135. So we get x squared plus 4x minus 5 equals 135. Now, if this were a linear equation, we'd take this -5 and move it over here, get all our constants to one side. Is that the strategy we do with a quadratic? No, what do we want in a quadratic? Equals 0. We need this to be set equal to 0. So I'm going to subtract 135 from both sides. And now I have to solve a quadratic. Easiest way to do this is somehow turn this into a product of two binomials. The trick we use for that is our diamond method. I'm going to put -140 on top. I'm going to put +4 on the bottom. Looking for two numbers that multiply to make 140, while at the same time add to make 4. Because this is a negative, one's going to be positive, one's going to be negative. Therefore, this is really the difference between those numbers. So as I envision all the various factored pairs of 140, 3 doesn't go in, 4 goes in, 5 goes in, 6 won't go in because 3 didn't go in, 7 goes in, 8 goes in, nope, 9, nope, 10, yep, 11, nope, 12, nope, 13, nope, 14, that's the same as this one. Okay, so those are my only possibilities. And if it multiplies to make a -140, then one's positive and one's negative. if when I add them together, I get a positive 4, will this column, the bigger numbers, be positive or negative? These will all be positive. These will all be negative. So I'm looking for one from this where the difference ends up being 4. These are too far apart. They're 139. These are 68. These are 31. These are 23. This one's just 4 apart. So that's what we're looking for. 14 times 10. My 14 is going to be positive. My 10 is going to be negative. So I'm going to rewrite this expression. X squared, instead of a plus 4x, I'm going to change it to writing it as 14x minus 10x minus 140 equals 0. Still the same, right? 14 and minus 10 makes positive 4. But I'm now going to do a factoring by grouping. So I'm going to take these first two terms, x squared plus 14x, and say what's common to both of them? X. So I'll pull that out. What I'm left with when I factor that out is x plus 14. Now I'm going to see what's common over here. What do you see common here? Right, I can factor out a 10, and because they both got a negative, I'm going to make it minus 10, and that's going to leave me x plus 14. And pro tip, what I'm looking for is these terms inside the parentheses to be the same. And what I can then say is, now what's common to this term and this term is the x plus 14. So I factor that out, leaving me with x minus 10. Because it's the zero product property, I can say that if these two things multiply together to make 0, that means either x plus 14 equals 0, so x equals negative 14, or x minus 10 equals 0, which means x equals 10. Algebra says we've got two answers. I got to look up here and make sure they both make sense. If I put a negative 14 in here, this is going to be 5 over negative 15. Overall, that's a negative number. If I put the same negative 14 up here, I get negative 9 over 27. That's also a negative number. So it works out fine. Both answers are valid. Any questions on solving these proportions, including some quadratic work? How are you feeling about the proportion part in general? 5, I feel confident I can solve these problems up here, no problem. Leave out the quadratics for a minute. 3, sort of, I'm going to have some refreshing to do, but I think I can get there. 1, this has always been hard for me. Great. Second part, the quadratics. 5, I can do quadratics, no problem, even if it has a lead coefficient of 2, like we'll see in number 20 over here. 3, I can do what you just did here. This is doable to me. If it gets more complicated, that's going to be rough. 1, quadratics is a gap I've got to work on. Okay, good. When you get to this one, what you're going to find is that the 2x plus 5 and the x minus 6 is going to give us a 2x squared. The only change is when you put these terms up here, you're going to have to multiply the 2 times the 140. So for example, in this case, it would end up being negative 280 up here. And the rest is the same. All right. The reason we're doing all this algebra in the middle of geometry is because we have to start talking about triangles that are not congruent, but are almost congruent. They're similar. Similar in the world of geometry is a very specific term. It means that it's the same shape, but it's been either blown up in scale or made smaller. Do you remember what the transformation scale was? We called it when it was the same shape, but shrunken or enlarged. Dilation. Yes, scale factor is what we use to describe that dilation. So for example, if this is 3 side length, and this is 10 times as big, 30, then if this side is 4, how big would this side be? Sure, it's 10 times as big as well. And I could do the Pythagorean theorem here. 3 squared plus 4 squared ends up being 5 squared, which means this hypotenuse would have to be 50. So what we're talking about when we talk about similar polygons is that they're the same shape, but potentially different size. Now, you'll notice that when these two triangles are scaled versions of each other, dilations of each other, that each of the sides is 10 times as big. Do the angles experience the same growth? They don't, do they? This 90 degrees doesn't turn into 900 degrees. So corresponding angles in similar shapes will be congruent. They're going to stay the same size, no matter how much it's stretched. A 30, 60, 90 triangle will still be a 30, 60, 90 triangle. But the corresponding sides are going to experience something else. If this one is times 10, then this one is times 10. Another way to think about that is if I take a ratio of corresponding sides, the ratio of any two corresponding sides is the same. Two ratios being set equal is called a proportion. So corresponding sides are proportional. They're in the same ratio. The ratio of those corresponding sides, like 50 over 10 or 40 over 4, is called the scale factor. And interestingly, if you add up all these parts and then add up all these parts, whatever the ratio of the sides was for similar figures, the perimeters are also going to be proportional. So for example, here I'm given two triangles. I can see that angle A and D are the same, and B and E are the same, and C and F are the same. That tells me that they're dilations of each other. That means that this side length of 8 is blown up to a size of 12, and 10 to 15, 14 to 21, etc. I don't love the way this is phrased, because it says, what is the scale factor of ABC to DEF? And what they mean by that is if I take triangle ABC over triangle DEF, I can say that that scale factor is the same as just taking any one measurement from ABC. Somebody give me one of these measurements, doesn't matter. 10 sounds great, too slow. If I pick 10, which is then the side that has to correspond with it from the other triangle? It's got to be 15, and you could do that number of ways. The least successful way would be to say it's in the upper right-hand corner, because that doesn't always hold true. You could certainly say that B and C are 2 marks and 3 marks, and E and F are 2 marks and 3 marks, so that makes sense. Lastly, you could use our statement here. We could say that if A, B, C, and D, E, F are written correctly, when we're comparing B, C, the last 2 letters, we should put in E, F, the last 2 letters. And of course, this reduces to divide by 5, 2/3. It's important to reduce it, because then when we talk about the scale factor of DEF to ABC, now we're talking about the bigger triangle over the littler triangle. Let's say I chose 21. I'd have to compare that to 14. And if I look at 10/15 and 21/14, it might be hard to compare those. Dividing by 7, we can say that it's 3 to 2, and we can see, oops, I got my ratio upside down. By the way, that brings up an interesting idea. I'm sorry to interrupt this thought process. But do you guys remember when you're given problems like 5/12 and 3/7? Which fraction is bigger? Five twelfths is? I think these are hard problems, but there's a very simple way to do it. What if this were a proportion? Then you could cross multiply. And if you cross multiply, you get 5 times 7 equals 3 times 12, or 35 equals 36. Is that true? No. That tells us what about these two proportions? There's two fractions, ratios. They're not congruent. They're not the same. So this question of which one's bigger is now more relevant. We know they're not the same. Now, if I look at the bigger of these two numbers, 35 and 36, 36 is the bigger one, right? Which two components contribute to make that bigger number? 3 and 12, good. The 3 of this bigger number is in the numerator. And generally in fractions, if the numerator is big, does that make the fraction big or small? Yeah, making the numerator bigger gives you more pieces of the pie. It makes it bigger. Whereas the denominator going smaller does what? Excuse me, the denominator going bigger makes the fraction smaller. You cut it up into more pieces of pie. So since this 36 is the bigger number, that means that relatively 3 is big and 12 is big. 12 in the denominator makes this number small. A bigger number in the numerator makes this number bigger. So 3/7 is the bigger value here. That comes up in like SATs and things like that. So that's a nice little trick. Could you also do it by making common denominators? Multiplying this by 12 and this by 12 and this by 7 and this by 7, and then comparing 35 is 36 over 84. And yes, this one has to be bigger. Either way works. Okay, what's the ratio of the perimeter of DEF to ABC? So we're saying the bigger one to the smaller one. What's that ratio going to be? Yeah, we can just steal it from here. This was also bigger over smaller. What we're saying is the perimeters are proportional just as the sides are. Last piece for today. You'll remember we've talked a lot about congruent statements. Right? Things like triangle ABC is congruent to triangle DEF. We've said that kind of stuff a lot. And that was a new shape for us at some point, a new comparative thing where we had a squiggly mark over an equal sign. And what this really means is that it's the same shape and the same size. If two objects are exactly the same shape, dilations of each other, and they're the same size, scale factor of 1, then they're congruent. But if they're just the same shape without having that number 1 as a scale factor, then that's similar. So it's just a little squiggly part to indicate that shapes are similar. And we can talk about congruent statements. We could say that, for example, up here, we could say that triangle ABC is similar to triangle. We need A to match with the one that's got its mark on it, B to match with its mark, and C, 3 marks to match with its. That's a similarity statement. And we can use similarity statements. They're really helpful in finding missing parts or identifying corresponding congruent parts. We said up here that corresponding angles are congruent. So angle K would be congruent to what angle? Good. If you look up here, you see that K is pinched in the middle. So what letter is pinched in the middle here? M. So K and M are corresponding parts. And yes, that shows us that this thing is spun around and confusing us. But using the similarity statements, it's super easy. L is then corresponding and congruent to what angle? N is correct. And what's the last pair? J and P. Could you have said P and J? Sure, because they're both congruent. However, let's go down to the sides now. Remember that sides aren't congruent. They're suffering some same scale factor in their change, which means that they're proportional. So JK, the first 2 letters, matches with or corresponds with what side length over here? PM. And if I take that ratio is the same as the ratio of what to MN? KL. And if that ratio were compared to the third side, it would be what over what? Sounds great. LJ could also have been Jake. L and NP. In other words, the first and the third, and the first and the third. Any questions on similar polygons and similarity statements? Your homework today is just to finish this packet submitted in Canvas. That's all we got. We got about 8 minutes left. You can get started on this. For those of you that need more effort on the tests, we can do that in class tomorrow. We can probably have time for you guys to take a stab at the test tomorrow.